Hello and welcome to yet another video for College Algebra. In this video, we will talk about graphing functions, and I mean all of it. We will take a look at most parent functions and how to graph them. I think the only one I don't get to is absolute value function. We will graph exponential functions. We will create a function equation from verbal descriptions. And we will take a look then at how exponential functions and log functions and their graphs are related. Then we will graph log functions and then create log functions from verbal descriptions. Strap in, I think this is going to be a long video. Let's get to it. On this slide, you can see that there are a variety of parent functions. We have them by name: quadratic, cubic, cube root, square root, linear, and constant. You can also see here we have parent function equations. So here f of x equals x squared, quadratic has to have an x squared in it. And in the rest of them, I hid them rather neatly here. F of x equals x cubed. That's a cubic function. The x has to be cubed. That is the defining feature for the equation. We have a cube root, where f of x equals the cube root of x, or the third root of x. Again, the cube, the 3 in the root here, is the defining feature for this particular parent function. We have a square root of x. Of course, that means we're going to have a square root symbol around the x, so the square root is the defining feature here. Linear, that just means we will have x to the first power, and that power 1 will be the highest exponent on x. And then constant. Constant is a little bit weird. There are no x's, just a single value here that makes this a constant function. So then very quickly, I want to go over all of the parent tables and parent graphs as well. So back to quadratic. This is the parent table for quadratic, and you can get any of these parent tables if you pick the numbers -2, -1, 0, 1, 2, and just substitute those into x. -2 squared is +4, there's your y value. -1 squared is 1, there's your y value. 0 squared is 0, there it is. And you can do this for quadratic, for cubic, for linear, and for constant. So you can see their respective tables here. -2 to the third power is -8. Quadratic, if you substitute -2 in for x, y would be -2. So on, so on, so on. And this one's a little bit odd because we're more or less forced to pick whatever number would have been here. So say this would have been equal to, let's say, f of x equals 5, then this would have been 5, and it doesn't matter what x we substitute in here, the y value, and remember f of x is the same thing as y, the y value is forced to be 5. The only two that do not fit this pattern are the cube root and the square root. And that's because you want to pick numbers that are perfect square numbers in the square root case. So 0, 1, 4, and 9. That way you can easily graph the y coordinates. Nobody out there wants to graph 3, square root of 3. I don't know what the square root of 3 is off the top of my head. But I do know what the square root of 4 is off the top of my head. So I choose 4 so I can move to the right 4 from the origin, 1, 2, 3, 4, and up to 1, 2, and I can have it graphed. And the same thing with the cube root. Cube root would be 8, 1, 0, -1, -8, and you can take the cube root of all of these numbers very easily, giving you this graph. So all of the graphs that we will look at when we start transforming them, aka moving them around, reflecting them around a coordinate plane, will start out here, 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 or here, based upon what type of equation you are given. You have to determine what the shape of the graph will look like. One other thing, the constant function here and the linear function here, you might be thinking to yourself, hey, those are both lines. You are correct. But if you think back to when you learned about describing graphs, when a graph was increasing, decreasing, or constant, a linear function will either be increasing or decreasing, and a constant function will be flat, just like we talked about with all of that before. All right, let's take a look at how to graph some of these parent functions. All right, so here we have how to move a graph. And this gets into some real funky notation. So we just have a times f of x minus h, and there's that subtraction of h in the parentheses with x. And then outside of the set of parentheses, we have plus k. So we have, where do I want to start? Let's start with plus k. So we can either add or subtract a number outside grouping symbols. So here's a set of grouping symbols. And you'll notice that the x minus the h is all inside a set of grouping symbols for the function. So if we can add or subtract outside grouping symbols, this will shift the graph up or down by y equals k units. So let me bring this a little more clarity. If we add a number outside of grouping symbols, we will shift up. And if you subtract a number outside of grouping symbols, you will shift the graph down. And it might not make too much sense right now, so I'll save more explanation for when I get into examples. Next, let's take a look at the other letter here, the other variable outside of grouping symbols, a. So with a, I had to put the description way down here. The only thing we deal with here is a being 1 or -1. So most of the time, it's either just going to be blank in front of our parent function, or we're going to have a -1 or a negative sign in front of our parent function. That's it. If a is -1, the graph is reflected about the x-axis. And again, you'll see a few examples of this as we move forward, so don't freak out if you don't understand yet. Lastly, we can take a look at this h, and in fact this minus h. This is the only operation that we will see in the grouping symbols. So if we add or subtract inside an actual set of grouping symbols with x, this will shift left or right by x equals h units. Now, here's where it gets a little interesting. If we have x plus a number, it will shift to the left. And if we have x minus a number, it will shift to the right. And of course, this has everything to do with what x should equal, not what is given to you. So let me give you this example here. If we had x plus 4, and especially if you have had any experience with synthetic division, you know that you can't just put plus 4 in the synthetic division, that you have to set the divisor equal to 0 and solve for x. Well, that's exactly what's happening here. So if you had x plus 4 in your grouping symbols, say you had f of x plus 4, and you wanted to tell me how is this graph going to move, you would have to set what is inside the grouping symbols equal to 0 and solve for x. This minus 4 then tells you would move left, even though we started with a plus sign in the middle, or in the beginning, in the grouping symbols. The plus sign in grouping symbols tells you to shift left. If you solve for x, it still tells you to shift left. It's similar to that. Let's take a look at 3 or 4 examples just to make sure you guys fully understand how this works. Example 1. We want to graph f of x equals the square root of x minus 4 plus 3. So the first thing we want to do here, and this is with all of them, you want to identify the parent function and the parent table. So what defining feature about this side of the equation do we have to work with here? Well, you mostly want to figure out where the variable is or what's happening to the variable. So I see the x is here, and I see a square root is around this x. So we can now know that the parent function is f of x equals square root of x, and that the parent table looks something like this. There we go. What do you do with this parent table? Well, you want to graph these ordered pairs as x's on the coordinate plane here. So you can kind of get the gist of where the parent function would be. So I'm just going to put tiny little x's right where the graph is supposed to be. And if you did connect these x's, you could see that it would look like the parent function for the square root function that we went over a couple slides ago. There we go, little note for you. The second thing you want to do is identify transformations. So identifying the transformations means outside of the square root of x, do you see any other numbers or any other signs on the right side of the equation? Well, yeah, I have a minus 4 and I have a plus 3. And I'm also going to mark the location of where these values are. So the minus 4 is inside. This is grouped up with x inside of a square root. Now, mind you, there are no parentheses here doing the grouping for us, but a square root does inherently group the x and the minus 4 into one expression. So the minus 4 is inside, the plus 3 is outside. And it is worth noting, maybe just once here, that any number that is grouped up inside with an x will create a horizontal movement or a horizontal change. And any number that is outside, not grouped up with x, will create a vertical movement, or we'll say a vertical change. Okay. So here we have this f of x equals square root of x minus 4 plus 3. We know these numbers are here. Horizontal movement, though, could mean one of two things. It could mean you're moving to the left. It could mean you're moving to the right. So going back a bit, we have a minus 4. Well, a minus 4 will make the graph shift right 4 units. And you can see that if you set the inside expression equal to 0 and solve for x. So the minus 4 will, we'll say, shift 4 units right. However, with the plus 3 on the outside, that doesn't change. That doesn't need to flip-flop. We don't have to worry about doing the quote-unquote opposite, because there's nothing, it's not grouped up in any set of grouping symbols. We already know it's 3. So that means the entire graph would also shift up 3 units. So how do we use this to our advantage, right? It says, oh, I already did this, plot the parent table with x's and graph the transformed function. That's the only other thing we have left to do here. So what we're going to do is we're going to take every single point with an x that we put here. We're going to move it to the right 4 units. So I'm going to take this x, I'm going to move it to the right 4 units, 4 units, 4 units, and yeah, we're going to be off the graph. That's fine, 4 units. Then what we do is we take all of those points and we move them from moving them 4 units to the right. We're going to take them and move them up 3 units. So I'll move it up 3 units, and I can start plotting my points now. Up 3 units, there's the next one. Up 3 units, there's the next one. Up 3 units, there's the next one. And these blue dots are what I'm going to connect, and that is where my new function is. That's how we moved the parent function to the right 4 and up 3. Now I've got to come back here. I've got to erase a little bit because these red movement lines, these blue movement lines, we don't have to write those down. There's an easier way you can do this. And as you can see, there is a starting point right here. This is where the square root function starts. So if we just move this one right 4 and up 3, we can start this new pattern here. Look, it looks like we go right 1 up 1, from this point, right 3 up 1, from this point, right 5 up 1. Look at this, right 1 up 1, right 3 up 1, right 5 up 1. We have the pattern. So you can see it. This parent function here was shifted right 4 up 3. The only other thing that we have to deal with here that you'll be asked to deal with is domain and range. We've got 4 to infinity for the domain and 3 to infinity for the range. One other thing that I would like to point out here is, take a look at this. This +3 was describing vertical movement. We went up 3 units, up, vertical. Those are all y directions. If you go move up, that's a y direction. If you move down, that's a y direction. Vertical movement is up and down. That's a, look, range is always describing y's. So it would make sense that we would see this number in the range. For the domain, it's not going to happen every time, but for this example, yeah, the domain here, we have a -4, positive 4. That's what you get if you set this inside part equal to 0 and solve for x. Just want to point that out. If there's a number in your parent function that wasn't there from the original parent function, it has a chance of ending up in your domain and range. All right, next example. We have negative x plus 7 cubed. And so the first thing we have to do is identify what is the parent function. What is the defining feature of the right side of this function that would help us graph this function? Let's see, we had quadratic, square root, linear, no, it must be cubic. I see an exponent 3. So let's get the cubic function, parent function, and parent table down here. There we go. I've got the parent function sort of hidden in the parent table. I've got my x's over here where the graph should have been. All right. Now we need to identify transformations. And I've got the first one here. I see it already. There's a number being added inside with x. So that +7, we don't have to set the inside expression equal to 0 and solve for x. We can just look. This +7, because I know this is positive, this is going to be a left movement. We will shift left 7 units. So that is one thing I see different, right? We have x cubed. What changed between this and this? Well, we added a 7 inside a set of parentheses with x being cubed. We also have this negative here. Let me do that with green. So the negative here, this is being multiplied to the function. When a negative is being multiplied somewhere, that's going to tell you there's some sort of reflection happening. And again, the only reflections we are looking at will be in in the very front of a function. So we have negative, which tells us to reflect over the x-axis. Now, the really cool thing here is that we have to follow the order of operations in order to make sure we plot the transformed function correctly. So we have to take care of any multiplications we have first. So we have to do the reflection before we do any additions or subtractions, before we do any shift. We have to reflect before we do any shifting. So a reflection over x, all it does is it takes any points that were below the x-axis, like this one, and reflects it to be above the x-axis. So you can see that the negative value here, this point is 8 units down below the x-axis. So to properly reflect it, we would have to move that point 8 units above the x-axis. So I'm going to put some green dots here, or green x's. This point is 1 unit below the x-axis. So if we were going to reflect it over the x-axis, it would be 1 unit above the x-axis. Points on the x-axis don't change, and points that are above the x-axis would move below the x-axis. So the green x's are the transformation after the reflection. The only other thing we have to do now is shift all of the green x's 7 units to the left. So here we go, 7 units left. And again, you don't have to draw the arrows. You can just count 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Move that left 7. Move that one left 7. Move that one left 7. There we go. That is the final resting place for our graph. So all we have to do is come in, draw it absolutely perfectly. There we go. That's not bad. And we have our transformed function. So again, then to finish up with the domain and the range, what we can do is we can just look at this and see that there are arrows going up and down at least. So arrows going up and down mean the range will start as far down as it possibly can, which would be negative infinity, and go up as far as it possibly can to positive infinity. And those arrows are also pointing left and right. Like this arrow over here is moving left and left and left and left forever. So the domain here will also be negative infinity to infinity. So I'm going to leave this one for you to try. You want to identify the parent function in table first. Again, find the characteristic that sets this apart from other functions. You want to identify all transformations, making sure that you take care of any multiplications before you do any addition or subtraction. And finally, you want to plot the parent function with x's, which I've been doing in step 1, and graph the transformed function as well. Go ahead, give it a shot. All right, here is the entire graph. Everything worked out for you. You can see we have the quadratic parent function in table. I plotted those with x's over here. It's kind of hard to see this one. But sometimes, and this one, sometimes points land on each other. That's why we use x's, so we know where only the final graph is here. We have to shift left 2 units, up 4 units, and reflect about the y-axis. So again, anytime you have a reflection, you want to do that first. And then, so the green x's here represent the reflection of the original black x's. Then we can do all the shifting at once. We can shift left 2 units and shift 4 units up. So from here, well, let's start here. From here I can go 2 left, 4 up, 2 left, 4 up, 2 left, 4 up. I can just follow that pattern indefinitely. If I had more points, I can shift them all 2 to the left and up 4. So I connect all of these, and this is the final resting place for this particular graph. Now, with the domain for any quadratic function, it's going to be negative infinity to infinity. That's fine. And the range here starts, remember we've got to start as low as we can. Arrows pointing down, that's going to be a negative infinity for sure. But the graph stops right here at a y value of 4. So here again, that number outside has a chance to show up in the range. The number inside has a chance to show up in the domain. It didn't this time because the domain was all real numbers, but it could happen in the future. All right, moving on to graphing exponential functions. This is what the point of this video is, to get the exponential graphing out to you. Let's see, we will have functions in the form f of x equals a times b to the x minus h power plus k. And again, exponential variable in the exponent, there it is. So we have a, h, and k, meaning all the same things they did before. B, you can see here, is highlighted in yet a different color. B is how we find our parent table, which is a really strange thing. If B changes values from problem to problem, the parent table changes values from problem to problem. So in order to figure out the parent table for an exponential function, the parent function first would be y equals b to the x power without an a, h, or k. And we can figure out the parent function simply by using the x's -1, 0, and 1, and then seeing what happens when we put these numbers into the exponent. So b, our base, just like any other base we've worked with an exponential video, the base has to be a positive number and not equal to 1. So as long as we have a positive number here that's not equal to 1, and we put a 0 in for the exponent, that number raised to the 0 power will be 1. Pretty simple. If we put 1 in for x, b to the first power is just b to the first power. Seems kind of simple. But if we put a -1 in here, well, now we would have a b to the -1, which means it would have to end up on the opposite side of the fraction. So there we go. I call this the reciprocal of the base. We flip the base. So we want to find the parent function and table. That should feel very familiar from the last few exercises we did. We want to list all the transformations and the horizontal asymptote. Oh yeah, exponential functions have asymptotes. So the transformations would be normal, like a equals 1 or a equals -1. If it's -1, it's reflected over the x-axis. And again, we would take care of that before we did any shifting. So h, this time being grouped up with x means it is in the exponent with x. Again, there won't be any parentheses there showing you any sort of actual grouping, but the exponent groups for us. And then we have k shifting the graph vertically. And then this is new. We have a horizontal asymptote at y equals k. So we will just have to be wary that we are plotting asymptotes, because we always want to put the asymptote on the graph before we do the actual graphing part, the x's and all that. So again, we will plot the parent table with x's, we will graph the transform functions, plot the horizontal asymptote first in both cases. This process should feel very familiar. We just have to actually create our parent table instead of memorizing a bunch of parent tables from the last few slides. Let's go. All right, first example, we have 3 to the x minus 2 power. And we want to graph this. So the first thing you want to do is write down the parent function and table. So that would look exactly something like this. We want to have x is here. We want to have f of x here. And the parent function is going to be the base and the exponent x. All right. So you are always going to have a -1, 0, and 1 for the x's. And how this will work is that 0 is always paired up with 1 is always paired up with the base, and -1 is always paired up with the reciprocal of the base. Now if you need to, and I didn't do this, and I will probably do this in the next example, you can write the base off to the side. That way you know what numbers are going here and here, the base and the reciprocal of the base. Okay, so there's that. The other thing here is that with any parent function for an exponential, the horizontal asymptote will be at y equals 0. So I'm just going to do this really quick. I want this y equals 0 here along the graph. And then I will put my x's here. So of course these 2 points are going to be the easiest to graph first. So 0, 1 is right here, 1, 3 is right here, and then the other point, whatever point ordered pair has a fraction with it, you'll just go over the correct amount. So in this case we'll go to the left 1. And then on the graph over here, we'll just put it really close to the horizontal asymptote. So this point right here is just going to be close to the horizontal asymptote the whole time. All right. Next, let's list out our transformations. Remember, a parent function is just supposed to be a base and the exponent x. So what's different up here? Well, the -2. But it works exactly the same way that -2 tells us we will shift, which way? We will shift right 2 units. So all of these x's are going to shift to the right 2 units. So what does that look like? Well, this one, I guess the very top x will end up here. That's 2 to the right. The x that I've placed on the y-axis will end up right here. And for this one, if I move it 2 to the right, it's still going to be very close to the horizontal asymptote. So it'll be right there. Cool. Last thing, draw the graph. And for exponential purposes, the graph will never cross the horizontal asymptote. So there it is. There is the graph of this exponential function right here. It was the parent function, right? Again, the parent function is just the base and the exponent x, shifted right 2 units. And when we're here, we definitely have to hit domain and range. So the domain for this one, I'm going to do it above the graph. The domain here is -∞ to infinity, because the domain for any exponential function will be -∞ to infinity. The range, however, the range is how low does this graph go? Well, this graph will get closer and closer and closer to, but never ever ever touch the horizontal asymptote. And so the horizontal asymptote is like a barrier for the range. So it is going to start way down there at 0, and we cannot include it. As I mentioned, it will never touch it. And then it will go up to infinity. So there is the range. Now, one final thing. Over here in this graph, or in the original function that was given to us, we can always find out what the horizontal asymptote will be if we look for the number being added or subtracted after the exponent. So here we have this, we have 3 to the x minus 2 power. If we wanted to write it in there, it would be plus 0. So the horizontal asymptote, even for the transformed function, is y equals 0. Now take a look at this really quickly here. When you start with this function, f of x equals blah, 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 whatever number is being added or subtracted there, even if you have to write it in as a plus 0 or think of it as a plus 0, that will end up being the horizontal asymptote for the transformed function. There it is. The horizontal asymptote here is still y equals 0. And this number will also show up in your range every time. And this is good for exponential functions. The number being added or subtracted here will always end up in your range and as the horizontal asymptote. Let's take a look at another one. Here we are going to graph negative e to the x plus 3 power minus 2. Couple things real quick. I can tell you the domain right off the bat. I don't have to even hesitate with that. Negative infinity to infinity. I can tell you even the horizontal asymptote at the end. Y equals negative 2. There it is. It's hiding right there. Cool. All right. What is the base? What is the exponent? We need to get a parent function and a parent table down on paper. So the base here, let me make sure to do this as I said I would. The base is e, which is about 2.71. We have x and we have an f of x equal to e to the x power. Now, we've started to pick up the big boy and the big girl math pants here. Negative 1, 0, 1. We are not using 2.71 in our table. We have to use e in our table. We have to use e over here in our graph so we can tell people where the points are. Luckily, if we still substitute 0 in for x, we get 1. If we substitute 1 in for x, e to the 1 power is e. The reciprocal of this thing here is 1 over e. For graphing purposes, all we are looking for is that this value, this y value, is between 2 and 3. And that this value, again, like I mentioned in the last slide, is just close to the horizontal asymptote. Cool. All right. So we have our parent function. Let's get this over here. The horizontal asymptote, again, for any exponential parent function will be y equals 0. So I'm just going to get it on the graph over here. There we go. 0, 1, somewhere between 2 and 3, close to the horizontal asymptote. All right. Next, we need to list out the transformations. That is, here is our parent function. Again, it's just the base with the exponent x. What's added to this function up here? Well, we have a plus 3. That seems to be grouped up with x, so we know we will be shifting left 3 units. Left 3 units, all right. We have a minus 2 back here, which we've already mentioned. You can see that we will be moving down 2 units. So down 2 units. And we have this wretched negative over here, which means we will reflect over the x-axis, or reflect about the x-axis. There we go. And as I mentioned in previous examples, you have to take care of the multiplications before you take care of the additions or subtractions. I mean, you just follow the order of operations. So I'm going to reflect all of these points over the x-axis, so maybe like right there, and right there. And again, what it does is it takes the distance from the x-axis and then puts it on the other side of the x-axis, that same distance. It's an actual reflection. It kind of looks like a mirror reflection. All right. From here, these are the reflected points. Let's move everything left 3 and down 2. And I'm going to do this in red, but before I move the points left 3 and down 2, what I really need to do is make sure that this horizontal asymptote also gets shifted left 3 and down 2. So if you take a horizontal line and you shift it left and right, it doesn't change the equation of the horizontal line. But if you shift it down, that's when it starts changing. And you can see here, this would be a horizontal asymptote of y equals -2, just as we mentioned right at the beginning. Y equals -2. You want to make sure you have the horizontal asymptote down first before you start moving your points. So I can say this point here, let's move it left 3 and down 2. So I know this middle purple X should be right here. So I'm going to put that in red right there. This X here is somewhere between 2 and 3, so if I move it left 3, that's no problem, but down 2, it has to be between these two and then these two, so let's put that there. We just can't put it specifically in one place, so you can see it moved left 3, 1, 2, 3, down 2, 1, 2, boom. This point, you can move it left 3, and then just make sure it ends up a little bit below the horizontal asymptote. There's not very much specificity going on here. And that's it. Those are the 3 points. We can connect those. There we go. And there's our graph. So we have to go back. We already talked about the domain. We already talked about the horizontal asymptote of the transformed function, which is really the only horizontal asymptote we care about. And we need that range. Now I can't all the time say what the range is right from the beginning, but I do know that -2 will be a part of it, that -2 will be a part of the range. In this case, the range starts at -infinity, you can see because the arrow going down forever. So the range here would start at -infinity and get close to 2 but never quite touch, -2 but never quite touch it. So again, you can see this shift, this vertical shift gives a lot of really good information over here for the horizontal asymptote of the transformed function and the range. All right, one more example. Here we have one final example for you, fractions, everybody's favorite. Say it with me. Fractions are your friends. All right, let's get to it. Parent table and parent function. So here we go. Parent table will always have -1, 0, and 1 for your x's. The y values, h of x, the parent function, is the base and the exponent. All right. The base here is 1/4, so 0 is always paired up with 1. 1 is always paired up with the base, and the -1 is always paired up with the reciprocal of the base, which in this case is 4. One last thing, again, the horizontal asymptote for any parent function is y equals 0. And you can graph it like this. You have the horizontal asymptote down first, 0, 1, -1, 4, right? You always want to graph the points with the whole number coordinates first. And then again for the last one where there's going to be a fraction, you want to go over the correct way, so 1 to the right, and then just put the point close to the horizontal asymptote, like this. Okay, listing transformations. We shift 1 unit left and 3 units up. I guess we can take care of some domain and range stuff right now too. I know the domain will be negative infinity to infinity. It's always going to be that. The horizontal asymptote now, that's pretty easy. It's just going to be y equals 3 because I see this number right here. There we go. Now that we know where this horizontal asymptote is supposed to be, we can place it. So we can start graphing our transformed function. So I'm going to place it and label it horizontal asymptote y equals 3. Now I can shift, and I'm going to do this with a red pen still. What do we do? Left 1 unit left and 3 units up. So this furthest left x, I'm going to move left 1 and up 3. So it looks like it should end up right here. The x that was on the y-axis, left 1 up 3. Oh yes, sometimes don't freak out if that happens. Sometimes points overlap. And then the last one, we know we're going to move it left 1 and that it has to be just above the horizontal asymptote. So it's going to be left 1 and right about there. So this graph will look something like this. Cool. So from here then we can talk about the range, right? We can't do the range until the very end most of the time. If you want to know how to find the range just by looking at this function, there's a way to do it. You're more than welcome to ask at any point. But there's the range. It starts at 3 and then goes up from there off to infinity. And then one other final note here. All of the bases that we've looked at in the past 3 examples have been bigger than 0. They've been positive numbers. But the shape of this graph is different. Left to right, it is decreasing. While the other 2 we looked at, left to right, they were doing something like this. They were increasing. So, if the base is bigger than 1, the graph increases. And we call this growth, exponential growth. And if the base is between 0 and 1, we can say the graph decreases. And that would be decay. And I should be a little more specific here. These describe only parent functions. This may be the only time you see parents only in any math video, but this describes only parent functions. If the base is bigger than 1, the graph increases. If the base is between 0 and 1, the graph decreases. So you can see here the base is 1/4. That's between 0 and 1. It's decreasing. We call that a decay graph. Again, in the previous 2 slides, the base was bigger than 1. 2 examples ago, the base was 3. Last example, the base was e, and both of those had this shape that looked something like this, going up left to right, whereas decay would be going down left to right. All right, so you learned how to graph. Let's see how else I can try to trick you with this stuff. On this slide, we have 3 examples. This time, no graphs. What's that? Yeah, I hear that sigh of relief out there. Good. So what we're going to be doing instead is we're going to be given a parent function, as you can see here. There's a parent function y equals 3 to the x power. And we're telling you what happens. It translated 2 units to the left. And you have to create the new equation. So like left, I know Left is a horizontal movement. That means it's grouped up with x. So I know I'm going to have to be putting a 2 up here with the x. So I'll make my new function y equals 3 to the x with a 2 up here. But then we have to figure out, is it going to be a plus or is it going to be a minus? Well, let's see. 2 to the left. If you look at a normal number line, there's 0. If you move 2 units to the left, that puts you at a -2. But x's are tricky like that. They want you to fall for this every single time. We have to do the opposite of that sign. Again, that goes back to, because the 2 is grouped up with x, we would have to solve for this x. So if we said x plus 2 equals 0, we now know that x equals -2, which is what this is referring to. So we have to play this little game that the signs are going to lie for an x movement. So this will be your answer for the first example. The next example, we have the graph of y equals 1 over 7 to the x power is reflected over the x-axis, translated down 5 units, and 3 units right. Okay, so we just talked about this. If you just write down the parent function, I don't think any teacher or professor will give you points for that, but that is like most of the answer right there. The only thing we have to figure out then is how to put reflected over the x-axis, translated 5 units down, and 3 units right, and add those things into this equation. All right, well, let's see here. Reflected over the x-axis, I think that's going to be the easiest one. That just means you put a negative in front of the parent function. Check. We just talked about the horizontal movements, a right or left movement. If you think of 3 being over here on the x-axis, moving right 1, 2, 3 would put you at a +3, but again, that's what x would equal, not what you need to get there. We would have to have a -3 up here. We need that opposite operation going on. And translated down 5 units, and this is where it gets really strange for students, is that down is a negative y movement. So any y movement we deal with is absolutely standard. It's the x's you have to watch out for. So this is our final answer here. The last one, we have the return of e to the x here. So again, if you just start writing the parent function, you're 50% of the way there. Then we just have to go again and figure out reflected about the x-axis, okay, and translated 3 units up. How do we represent those things in our equation? Well, again, reflected about the x-axis, pretty simple. You just throw a negative in front of the entire parent function. Multiplication by -1 is how we represent a reflection. You can see here this would be -1 times e to the x. We don't need the negative, we need the negative. We don't need the 1 here, so we can just call it -e to the x. All right, lastly, translated up 3 units. Up is a vertical movement, and that means this is a y movement. This will not be grouped up with x, so we can say +3. There we go. One last thing to round these 3 examples out. We should be able to list out the horizontal asymptote for all of these. The horizontal asymptote for example 1, I think, is just at y equals 0. Yeah, there's no number being added or subtracted behind the base with the exponent. This number is in the exponent. We need a number that is out back. Let's see here. The next one, we have this -5, which leaves us with horizontal asymptote y equals -5. And then with the last one, we can see there's a 3 here, so the horizontal asymptote would be y equals 3. Again, you can just read it right from the equation. All right, time to switch gears all the way. Let's take a look at how log graphs work. In order to get a good understanding as to how log graphs work, we need to first see another graph of an exponential function, say f of x equals 2 to the x power. No transformations, we're just going to look at the parent. So we know that -1 is paired up with 1 over the base, or the reciprocal of the base, in this case is 2. 0 is always paired up with 1. 1 is always paired up with the base. Now I went a few points extra here, so I substituted 2 in for x. 2 squared is 4. I substituted a 3 in for x. 2 to the third power. 2 times 2 times 2 is 8. Just to get this graph a little bit of a longer line here, a longer curve actually graphed. We know that the horizontal asymptote for any exponential parent function is y equals 0. We can also talk about the domain and range here. So the domain is -infinity to infinity. Fantastic. The range is 0 to infinity. Sweet. How does this correlate over to a log graph? Well, to spill all the beans, logs and exponentials are inverses. And the big deal with inverses was that you swap all of the x's and all of the y's. So I'm going to make a log table here. Let's see, we would have x, and remember the base of the exponential function will be the same as the base for the log function. So let's call this f inverse of x. There we go. So how does this work? We have all of the x's becoming the y values, 1/2, 1, 2, 4, and 8. And then all of the x's, the y's are now the x's. Let's see, -1, 0, 1, 2, and 3. All right, let's see if I can work some magic here. This works with domain and range as well. So all of the x's become y's, and all of the y's become x's. So I'm going to predict that the domain for this log function will be 0 to infinity, and that the range will be all real numbers. It even works for asymptotes. Anything that has a y in it becomes an x, and anything that has an x in it becomes a y. So I'm going to change my asymptote here to x equals 0. Now, something to be said about this, when we were looking at rational functions not that long ago, horizontal asymptotes were always y equals some number. Vertical asymptotes were x equals some number. So this changes to be from a horizontal asymptote to a vertical asymptote. All right, let's see what happens here. Let's graph all of these points and just talk about it a little bit more from here. So let's see, I've got 1/2 -1, which means I go over a little bit and down 1. So I've got that point there. 1, 0, that's this point here. 2, 1, that's this point here. 4, 2, that's this point here. 8, 3, that's this point here. And it looks like I can connect these points like this. And I know I cannot go past the y-axis here because I have a vertical asymptote at x equals 0. So let me get that in here. There we go. And yeah, it looks like the range, this is going to go down forever. This is going to go up forever, -infinity to infinity. The domain gets close to 0, but never ever gets quite to equal 0. So parenthesis 0, it goes to the right forever, infinity, yeah. We have a vertical asymptote at x equals 0, yeah. Oh, yeah, here is another thing about inverses. Remember this? Inverses are a reflection over the line y equals x. And you can see that the reflection here is pretty good freehand. This is a mirror image over this line y equals x. Let me write the equation of the line here. Y equals x. And that's like the key to graphing log functions, is knowing that if you can find the exponential piece parent table, you can swap the x's and y's to get a log parent table, and then you have to find vertical asymptotes, which I will go into on the next slide. But a vertical asymptote for a log parent function, which is a log, a base, and an x in the argument, is always going to be x equals 0. So this is very, very powerful, and this is what makes graphing logs very, very simple, is that we can relate it back to exponential functions. All right, let's take a look at some specific examples on how to do this. Example 1, we want to graph this function f of x equals log of x plus 4. And in this case, it's pretty simple to see that the plus 4 is grouped up with the x. So the very first thing we want to do here is we want to create the exponential table. The only problem is we don't know what the base is supposed to be. Normally a base for a log is written right here. Luckily, you can remember that if there is no base, given anyway, the base is 10. So the exponential function here that goes with log base 10 of x is 10 to the x power. So we know the base is 10. So 0 is always paired up with 1, 1 is always paired up with the base, and -1 is always paired up with the reciprocal of the base. Now here is a funny thing about this. We are trying to graph a log function. You can tell because there's a log in the function. I know. Anyway, this is not a log table. This is an exponential table. So an exponential table, which I've already gone over, is pretty easy to compute, needs to be transformed into the log parent table. And the log parent table would be x equals, x and f of x equals, now we only want the log, the base, and the x inside the argument. There we go. But it's real easy. We already have the log table. It's right here. We just have to turn all of the x's into y's and all of the y's into x's. So here we go. We have, let's see, 1, 10th, 1, and 10. And then we have -1, 0, and 1. So again, all of these x's became the y values, and all of these y values became the x values. Cool. So I want to go ahead and place x's on the coordinate plane at these ordered pairs. Oh, but wait. We also have to remember that every log parent function has a vertical asymptote at x equals 0. Let's make sure we get that in there first. That'd be like right here, right down the y-axis. There we go, vertical asymptote, x equals 0. And we're going to graph these a lot like we did with the exponential table. I always graphed these points first, the one without the fraction, because those are going to be the easiest. So I'm going to graph these points first. So let's see, that is 1, 0, which is right here. I've got 10, 1, which is way over here, and I have 1/10 comma -1. Now the -1 here, y-coordinate, is super easy. We just have to go down 1. But kind of like we did with the exponentials, this is just going to be very close to the vertical asymptote. Cool. All right, so again, this is the table we are after. This is the actual log table. All right, next, transformations. I see one extra number here, this +4. That +4 tells us we are going to be moving left 4 units. Right? I mean, it's inside a grouping set of grouping symbols with x. And there it is. I mean, we're going to be moving left 4 units. But everything about this graph moves left 4 units, including the vertical asymptote. So the vertical asymptote will move left 4 units right there. All right, we have this first point, 1, 0, moving left 4 units, 1, 2, 3, 4. That's right there. We've got this point right here, 10, 1, moving left 4 units, 1, 2, 3, 4, right there. And then this point here is also moving left 4 units, but you can see this x is just a little bit to the right of the vertical asymptote. So the final resting place will just be a little bit to the right of the vertical asymptote. Cool. All right, so there is the graph. The blue graph is there. The vertical asymptote for the blue graph is x equals -4. We can talk about the domain and range. Again, for log functions, it's kind of like the domain for the exponential functions. We don't have to really think about it too much. We know the range is going to be -infinity to infinity. The domain here we can figure out will be, how far left does it start? Well, we're not going to go past -4, so we can start at -4, and then it'll go off to the right, off to infinity. So let's see, -4 to infinity. And then we can also talk about the vertical asymptote. Let's see here. So the VA, I know it's listed down there. I just want to have it all in the same place. So x equals -4. All right, one last thing to point out here before we go on to the next example. You'll notice that whatever is inside with x here, the argument, if you set that equal to 0, this tells you, and solve for x, that tells you so much. If you set the argument equal to 0 and solve for x, you get exactly the vertical asymptote. You know the number that will be in the domain. And really also, it tells you how far left or right the graph is going to move. So we all know that if you just look at this, +4 means move left 4 units, as we described down here. But again, it's because when you solve for x, when we go from x equals 0 to begin with, and then add 4 to everything, that means we have to solve for x, and the -4 tells us move left 4. All right, let's take a look at the next one. Here we have example 2, graph the function p of x equals the natural log of x minus 7. Now you'll notice that there are no parentheses on the right side of this equation. What that means is the natural log only will accept the first term after the natural log notation. So if we just forget about this here for a second, let's see, if we just forget about this here for a second, this natural log, you can see that there are 2 terms. The first term being x, the second term being a -7. So it's almost like we have implied parentheses around the x. So this -7 is not in the argument. All right, here we go. Exponential table and log table. Here they are. So it is important to remember that the base for this log function is e. Natural log has base e. All right, so what we can do then is we know that the base for the exponential part of this will be e. So again, 0 is always paired up with 1. 1 is paired up with the base. -1 is paired up with the reciprocal of the base. So all we have to do then is make sure that when we make our log parent table, all of the x's become the y's, all of the y's become the x's. Cool. How do we do this? Oh, before we go too much further, we better make sure the vertical asymptote is x equals 0, because that's what it is all the time for a parent function. So let's get that vertical asymptote in here. There goes the vertical asymptote. Awesome. Let's get these points in here. 1, 0, of course, is going to go right here. E comma 1 means we go over to the right between 2 and 3 and up 1. And then 1 over e comma -1 means we just go down a little bit. I mean, we go down 1, but we just go to the right a little bit. Again, it's just going to be close to the vertical asymptote x equals 0. Now we do our transformations. This -7 here, that -7 means we shift, which way do we go? We shift down 7 units. All right, so let's talk about the vertical asymptote first. We have a vertical line. If you move it up or down, it doesn't matter. It's still going to be the same vertical asymptote. So let's get the new vertical asymptote graphed in here. Again, it's going to be vertical asymptote x equal to 0. Now we can just move these points straight down. So I'm going to move this leftmost point down 7. 1, 2, 3, 4, 5, 6, 7. It should go right there. Notice it is still between 2 and 3 because we did not move any horizontal direction. The next one, we can go down 7. That'll put me right there. And the last one will go down 7 as well. It started at -1. Look at that. It started at -1. If we go down 7, we should be at -8. And that's a good way to think about all of these. This started at a +1 y value. And if we go down 7, we should be at -6. Yeah, that makes sense. All right, let's connect all these together like this, like this. So we can have the domain. Well, let's do the range. The range is going to be easier. -∞ to infinity. Don't think about it, just write it. The domain, oh look, definitely has to do with the vertical asymptote. And look at this even. Oh yeah, vertical asymptote is an x equals something. X. Domain deals with x's. Look at that. So 0 to infinity. And then we already understand the vertical asymptote is x equals 0. One more example. Okie dokie. Let's get it. The function here is r of x equals negative log base 1/2 of x minus 5, all in parentheses, plus 2. All right. Just see if you can come up with the parent tables right now. The exponential parent table and the log parent table. Go. All right, here I have the tables and
the corresponding x's over here on the coordinate plane with a vertical asymptote of x equals 0. Again, the vertical asymptote always starts out as x equals 0 for the log parent function. Now, there are 3 transformations here. See if you can figure out what those are. Okay, here I have them color-coded. The blue circle here for reflect over the x-axis or reflect about x-axis. I've got the -5 here in green, which would tell us to shift 5 units to the right. Again, even though the -5 looks like it's over here, it is actually telling us to move to the right, because if you set the argument equal to 0, you will get x equals 5. So we're moving everything to the right 5 units. And here the +2 tells us to shift 2 units up. So as always, we need to reflect before we do anything else. And again, we will be reflecting over the x-axis, so this point will end up being right here. This point stays right where it is, and this point ends up being right here. So we have these 3 points, and they do look like they are going to form a line, but I promise you they are not going to form a line, and I will show you how to draw this in just a moment. From there, we will shift each unit to the right 5 units, and then each point up 2 units from there. So I will put the final graph here in black. So from this point here, we will move it 5 units right and 2 units up. So 1, 2, 3, 4, 5, 1, 2. There's 1. Oh, where would the vertical asymptote be? If we move the vertical asymptote to the right, it'll be right here. There we go. All right, that's going to help us with the placement of our points. So then I'll move to the next point. Let's see, this point will move 5 units right, 1, 2, 3, 4, 5, and 2 units up. It'll be right there. And the last point here, the blue point, right? The blue points are the reflected points. So we'll move it 5 to the right and 2 up, and it'll be about right there. Now, how do you draw this so that it looks curvy and not linear? Well, the graph is always going to get close to the vertical asymptote, and then it almost flattens out as you move to the right. And that's it. There's the graph. We can talk about the domain and range and vertical asymptote. We've already mentioned what the vertical asymptote is here at x equals 5. And again, you can find that if you set the argument equal to 0 and solve for x. The vertical asymptote would be x equals 5. So the domain here would start at, what do we do here? 5 to infinity. And the range, don't even think about it, all real numbers. So if you like using the double bar r, that's fine too. One more slide, let's get it over with. All right, here we're looking at making the equations, the new equations out of the parent function. So again, we have a parent function here. We get some description about it, in this case translated 15 units to the left. What would that look like? Well, left and right movement is an x movement that we need to group up with the x in some kind of grouping symbols. So this would be x and 15. But we would have to add the 15, because if you set this equal to x, then you can see that it would be x would equal -15, which would be the left movement here. Also list the new vertical asymptote. So if we take that x plus 15 inside, set it equal to 0, we would get x equals -15. Boom, there's your new vertical asymptote for this transformed function. And the rest of these work the same way. So if we have the graph of y equals log of x is reflected over the x-axis, so there's one that I can see. Let's see, reflected over the x-axis, translated 67 units down and 95 units right. Ooh, that's a lot. All right, so we have this here. What does that even mean? Well, that means we are going to have y equals log of x. And remember, if you just write down the parent function, you can more easily set up what you need to do for this exercise. Reflection over the x-axis is still a negative in front. Translated down 7 units, that's a vertical movement. Let's put that way out back, something like this, because that will not be grouped up with x. But a left and right movement, as you can see here, will be grouped up with x. So that 95 needs to be in parentheses with the x, so we can take the log of all of that. But what are we going to have to put in there? Well, first a 95, but moving to the right means we should have a negative in there. So it would be x minus 95. And again, if you set the argument equal to 0 and solve for x, you would get x equals 95 as your new vertical asymptote. So this is the new equation. This is the new asymptote. Just like in the last example, here's the new equation, here's the vertical asymptote. For the last one here, it's pretty straightforward. We'll have y equals log base 1/2 of x. And we have two transformations here. I see reflected about the x-axis and translated 31 units up. So up is not a horizontal movement. Up and down is vertical, which means it's a y movement. So we do not put that in parentheses with an x. Reflected over the x-axis is a negative in front, and the new vertical asymptote here is the same as the old vertical asymptote because we did not move it left or right. The vertical asymptote stays exactly where it was at 0. All right, I hope that was understandable. I hope this gave you a better, deeper understanding of logs, hopefully made them less scary for you, and I wish you luck.